A confidence interval can look precise and still be the wrong band for a future prediction. We'll derive both in NumPy, so you know which uncertainty your model is actually reporting. You'll see how to connect the pieces into a workflow that compares interval coverage and chooses the right uncertainty band. I'm Professor Pi, teaching AI foundations with simple Python. Prediction intervals and confidence intervals both show up when you want numbers plus honest uncertainty. Practically, this means you trained a regression, and now you need to answer two different questions. One question asks, what is the average outcome at an input? The other asks, where will a single future observation land? They look similar on a plot, and that's why people mix them up. That mix-up matters in product decisions, experiments, and reporting, because the wrong band gives the wrong sense of risk for a single user or measurement. Intuitively, a confidence interval asks where the true mean likely lives. A prediction interval asks where the next noisy observation will land. The prediction band is always wider, because it folds in the extra random noise of a single draw. Picture a fitted line through noisy points. The mean band hugs the line. The prediction band adds the cloud of individual points around it. We will build a tiny NumPy workflow that fits a simple linear regression, inspects how uncertainty changes across X, and shows why the prediction band is safer for one-off forecasts. This keeps the math minimal and uses plain NumPy so you can reproduce it in minutes. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we fit the simplest regression, so we have a baseline model to examine uncertainty around. This snippet fits the smallest possible regression line for the lesson. The toy X values are easy to read, and air adds visible noise, so the data is not perfectly clean. NumPy builds the design matrix X with a column of 1s for the intercept and a column for X. Then np.linalg.lstsq estimates B, where B at index 0 is the intercept and B at index 1 is the slope. The code prints those parameters so you see the fitted line. That gives us a shared model before adding uncertainty bands, and lets us talk concretely about residuals and leverage in the next steps. Now we separate two different uncertainties and show they are numerically distinct. This example separates uncertainty about the average response from uncertainty about one new response. The residuals estimate sigma, the typical leftover noise around the fitted line. NumPy uses np.linalg.inv on x.tx to measure leverage for the point V, representing predicting at x equals 1. The confidence interval half-width uses h, while the prediction interval half-width uses 1 plus h, because a new observation also carries fresh noise. The printed result compares both widths, and you will see the new observation band is wider, which is the core warning against using a mean interval for a single prediction. Next, we inspect how interval width changes with where you predict, not just the band type. This code compares uncertainty at the center of the data versus outside the data range. The matrix V holds 3 candidate prediction locations, and NumPy computes each leverage value in hgrid for those locations. A confidence interval for the mean grows when leverage grows, so points far from the observed X values get larger CI widths. The code uses np.argmin on CI widths to pick the tightest location and prints the ordering so you see which X is safest for mean estimates. The result shows the center is the narrowest mean band and the edge band is noticeably wider, which affects where the model is reliable. Now test what happens when you ask the model to cover actual, new, noisy observations. This snippet checks what happens when the target is a future observation, not the fitted mean. Future Z is a small deterministic sweep of possible new errors built with NumPy np.linspace. So the output is stable on screen. For each candidate future error, the code checks whether that future value falls inside the confidence band and inside the prediction band at center. The comparison CI cover versus PI cover shows that the confidence band was never designed to contain new noisy observations, so it misses many more cases here. The printed counts make that gap clear and drive home why the prediction band matches the prediction question. Finally, turn the idea into a tiny, reusable function you can call at NEX. This example turns the lesson into a tiny, reusable baseline. The function interval takes XO and target, then computes the fitted center mid, leverage lev, and the needed half width. When target is mean, extra is 0, so the band answers uncertainty about the average response. When target is new, extra is 1, so NumPy np.squared includes the extra observation noise for a prediction interval. The function prints the selected mid and half width for the requested x0, and the output shows the selected band for a new prediction at x equals 1, which is the safer choice for a single future value. If you map this toy code to a real project, use the same pattern but with larger data and a proper train test split. Fit with the real feature matrix, compute leverage with x transpose times x on the training set, and evaluate coverage on held-out futures to make a decision about reporting bands. 3 clear takeaways. First, a confidence interval reports uncertainty about the mean, not a single new observation. Second, a prediction interval adds observation noise and is the correct band for forecasting one future value. Third, watch leverage. Predictions far from your data get wider intervals and less trust. Try one concrete next step. Evaluate interval coverage on an actual dataset, such as the Boston housing set. And tune whether you want to report mean or new observation bands for each user request under real sampling variability. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.